seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Okay, we got a roll program.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading. Altitude's 2 miles.
Oh, well, Houston, you're good at 1 minute.
Downrange 1 mile, altitude 4 miles now.
Around the Earth there are radiation belts which have been named by the scientist who discovered them, Van Allen. These belts contain radiation which are dangerous for man, especially in the heart of these rings. Some think that once these belts have been passed there is no more danger, but it is completely wrong, for these are not these belts which create radiations. The radiations in fact come from solar eruptions, and these belts stop them and protect us from them. After these belts have been passed, there is no more protection against these radiations, so the danger persists. It depends of course on the current level of the solar eruptions. This is the table of the occurrences of the solar eruptions for the various Apollo missions. Robert Bray-Unick has imagined a trajectory that the command module would have taken and which would have allowed it to avoid the dangerous part of the Van Allen belts and would have spared its radiations to the astronauts. This trajectory had been shown by many Apollo believers like it was gospel, and nobody doubts that the command module really took this trajectory. The problem is that there is not the least document of the time of Apollo which confirms this trajectory, and, still worse, there is even a document which outright contradicts it. This document, which contradicts the trajectory of Robert Bray-Unick, is entitled Apollo Launch Windows. This document shows the trajectories which would have been taken by the Saturn rocket. But what really interests us is the trajectory the command module would have been put on. The document clearly states that this trajectory depends on the position of the Moon on its orbit. This position is not constant, and while the command module travels, the Moon travels on its orbit. So in order to optimize the trajectory and make the minimal maneuvers, the goal is to direct the command module not towards the current position of the Moon, but towards the position it will have when the command module has reached it. The Moon orbital plane mates with the elliptic plane, the plane of the orbit of the Earth around the Sun, an angle of 5 degrees, which is to be added to the angle then the elliptic plane mates with the equatorial plane of the Earth, which is 23 degrees. So in total, 23 plus 5 equals 28 degrees. The document shows a graph which represents the direction of the Moon relatively to the equatorial plane of the Earth as a sine wave of amplitude 28 degrees, the angle between the orbital plane of the Moon and the equatorial plane of the Earth. That is why it's important to study the evolution of the Moon on its orbit in order to determine the optimized trajectory, the one which will direct the command module directly to the position that the Moon has when the command module arrives near it. So, the whole problem is to know where the Moon will be on its orbit at the moment when the command module reaches it, in order to determine the direction it must take at the beginning of its travel. We know that the command module of Apollo 11 reached the Moon on July the 19th. In order to know it, we have to look for the previous new Moon and the previous apogee, so to be able to determine where it was on its orbit at this moment. And when we check it, we can see that the new moon preceding Apollo 11 happened on July the 14th, so 5 days before the command module reached the moon. And when we check the apogee for preceding Apollo 11, we find that it happened on July the 13th, for 6 days before the command module reached the moon. We know the moon takes 7 days to travel a quarter of its orbit. From what we have just seen, it means that the moon was at the moment much closer to the equatorial plane of the Earth than the peak of its orbit. It means that the angle that its direction was making with the equatorial plane was consistently less than the angle between the orbital plane of the moon and the equatorial plane of the Earth, hardly a quarter of it. In fact, the SIVB was not only given an initial speed to the command module, allowing it to get away from the gravitational field of the Earth, but also an initial direction corresponding to the position of the moon would have when it would reach it. When the command module was just following this direction with its engine off and was making no change of direction before the point of the first mid-course correction. In Apollo 11, the point of first mid-course correction was at a very low latitude, which means that it was quite close to the equatorial plane of the Earth. If we draw lines between the point that the command module left the SIVB and the point where the command module reached the point of the first mid-course correction, without having to use its engine between these 2 points, in the various missions in Apollo, using the data we find in the mission reports, it gives what this animation shows. You can see that the command module systematically goes into the heart of the radiation belts. It never tries to avoid them. If the command module had tried to take the trajectory advocated by Robert Brownlee, it would have had to consume plenty of propellant to make all the changes of direction, and it would have burnt so much of it, it would have been short of it even before reaching the moon. It was completely contrary to a reasonable consumption of the propellant. If the astronauts had gone around the Van Allen belts, perhaps they would have been spared the radiation, but they would not have had enough propellant to come back to the Earth, and they would have ended up lost in space, which is hardly better than not suffering from radiation. NASA has shown tables of re-entry parameters for the various missions. The flight path angle is the angle under which the spaceship penetrates into the atmosphere. It is obvious that the greater it is, and the faster the command module will descend. However, this angle must not go beyond some limit, otherwise the descent speed would be such that it would cause fatal overheating for the command module. The re-entry parameters are not easy to study when directly read in the table. That is why they have been here represented in the form of supposed graphs. For each graph, the lowest ordinate coordinates to the minimal value of the parameter, and the highest ordinate to the maximal value of the parameter. The horizontal axis corresponds to the missions Apollo 11 on the left to Apollo 17 on the right. The Apollo 13 mission, corresponding to the blue vertical bar which has been represented, is particularly interesting. It has a greater flight path angle than in the previous missions. It also has a smaller duration, which is logical, for this greater flight path angle made the command module descend faster. But while it should have also had a greater maximum G measures the acceleration or deceleration, greater heating parameters and also higher radiation dose than the previous missions, it illogically appears to be the converse. All these parameters have varied in the wrong direction. And if we compare Apollo 11, left of the graph, with Apollo 17, right of the graphs, we can see that Apollo 17 has a consistently smaller duration than Apollo 11, which means that it's descended faster, greater heating parameters and greater radiation dose, which is compatible with a faster descent. But while we'd expect Apollo 17 to have a greater maximum G than Apollo 11, it illogically has a little smaller one. We can find other incoherencies in this table which cast a serious doubt on these re-entries. Then you are going to say, if the command module did not return from space, then how is it that we could see it go down with its parachutes? It was simply dropped from a cargo plane flying at high altitude over the clouds. It was dropped like in this test. You can notice that in this test the parachutes are dropped in the same time as the command module. They don't deploy from the module. If the parachutes could deploy from the module, then why didn't they show it in this test? and we can wonder how so big parachutes could hold in so small compartments. In the videos of Apollo, the spaceships behave in a completely abnormal way. For instance, in this sequence of Apollo 15 filmed from the lunar module, we see the lunar ground which shifts completely fast and slow, which suggests that the orbital speed of the command module and the lunar module would change in a completely impossible way. And in the videos and photos of Apollo, while the command module and the lunar module are flying one above the other for some time, before the lunar module starts its descent on the moon, it is the lunar module which is above the command module, while we would rather expect the converse. And on this photo of Apollo 11, AS11 37 5447, we can also see the command module, which is far under the lunar module. And if we make a close-up on it, we can effectively see that is the command module. But why the command module have gone so far under the lunar module? It is absolutely obvious that the nozzle of the service module was lighter than the rest of the command module. This fact will place the centre of the mass of the command module above its geometrical centre when it is orientated up. When the centre of mass and the geometric centre of the satellites are not confused, this satellite naturally orientates itself so the centre of mass and the geometric centre are aligned with the direction of the centre of the body of the satellite's orbit, whether it is the Earth or the Moon, and the centre of mass closer to this body. This comes from a physical principle called gravity gradient, and it is explained by the fact that the gravitational force varies with the inverse of the square of the distance of the satellite to the body's centre, while the centrifugal force varies with the simple inverse of this distance. Consequently, when the satellite gets away from the body, the gravitational force decreases faster than centrifugal force. It means that if the centre of the mass of the command module is closer to the cone of the command module than the geometric centre, the command module should naturally orbit the moon so that the cone of the command module is orientated downwards and not upward. So the command module should not orbit the moon this way, like what we see on the videos. But this way, with the cone of the command module orientated towards the moon. Of course, these animations are symbolic and respect neither sizes nor distances. Now you understand why it was the command module which had to be under the lunar module and not the opposite. On this animation made with the successive photos of Apollo 14, we can see the lunar module, which wildly turns over as it gets away from the command module. Of course, it could turn over so that the pilot of the command module could inspect it before it starts its descent on the moon. But it should then remain close to the command module while it turns over, and not get in the way at the same time. What we see here is completely illogical. Some have compared the lunar module with a plane or a helicopter, but its behaviour is completely different from the one of a plane or a helicopter. Indeed, the lunar module has no wings, which would be completely useless in the void of the moon. While a plane passively uses the force of air to control its attitude and to sustain itself in the air, the lunar module controls it actively with its engines, and the control is extremely different. The lunar module was initially too far from the lunar surface to start the powered descent, so it is starting to take a descent orbit to reach an orbit closer to the lunar surface from which it could start the powered descent. This manoeuvre was consisting in decreasing a little its orbital speed in order to put itself in an elliptical orbit, allowing to reach this closer orbit. This manoeuvre was called DOI, Descent Orbit Insertion. After the initial manoeuvre, the lunar module was just gliding in this orbit with its engine off. In this sequence of Apollo 12, we can see the lunar module making this manoeuvre. We can be sure that it is currently reducing its orbital speed, for we can see the lunar horizon appear at the end of the sequence, the black which appears over the lunar ground. It means that the camera of the command module is turning to follow the lunar module getting away from it. So, if the camera of the command module turns to follow the lunar module, it means that it should see it under a different angle. Yet, on this video, the camera keeps seeing the lunar module under the same angle, like the lunar module was still at the vertical of the command module. This sequence is thus unrealistic. When the lunar module has reached a closer orbit, it starts the powered descent, which means that it's going to use its engine at full thrust initially. During the initial phase, the lunar module is orientated horizontally because it must use the thrust of its engine to counter the horizontal velocity and make it decrease. Initially, the centrifugal force allows the counter the lunar attraction, which means that it does not need to be countered. Progressively, as the LM loses its horizontal velocity, the centrifugal force decreases, which means the lunar attractions tend to be more and more attract the lunar module towards the moon and make the vertical speed increase. But during the initial braking phase, the vertical velocity remains small relatively to the important horizontal velocity and represents only a hundredth of the horizontal velocity or around it. So in this phase, the lunar module ignores the lunar attraction and concentrates the thrust of the engines, essentially decrease the important horizontal velocity, which means it remains horizontal. After this phase, it starts turning to vertical in order to start countering the lunar attraction before the vertical velocity becomes too important. Moderately at first, and then more and more as the horizontal velocity becomes smaller and smaller, to end up completely vertical at the end. This change of attitude must be very progressive and can in no way be brutal. When the lunar module is close to the lunar surface, its horizontal speed is very moderate. If it was not, there is no way the landings could have succeeded, and the lunar module could not benefit any more than centrifugal force, and it must counter the lunar attraction with its main engine. If it was turning horizontal at that moment, it would be attracted by the moon and crash on it. The physics of the ascent is exactly the same as the lunar module, but inverted. It has to turn slowly and regularly from a vertical altitude to a horizontal one, to leave the time and centrifugal force to grow enough to be able to sustain the lunar module in space. This sequence, in which we see the lunar module suddenly turn from a horizontal attitude to a vertical one just before landing on the moon, makes absolutely no sense, for when the lunar module is close to the lunar surface, it has a low horizontal speed and has lost the centrifugal force which was allowing it to counter the lunar attraction, and it does not benefit of air force to sustain it, like for a plane or a helicopter on Earth, which means it can only counter it with its main engine, and it must absolutely have a vertical attitude for its main engine to counter this attraction. Its lateral engines allow it to make for maneuvers of rotation and translation, but they are not powerful enough to counter the lunar attraction, and moreover their thrust cannot be adjusted. If the lunar module was flying with a horizontal attitude, it would not be able to counter the lunar attraction, and it would be attracted by the moon and would crash on it. And even if the lateral engines had been powerful enough to counter the lunar attraction, and their thrust could have been adjusted exactly to counter the lunar attraction, the lunar module would not have been able to remain perfectly stable like what we see on the video, when it is turned from a horizontal attitude to a vertical one. So, this video does not make the least sense. It is physically impossible. In the liftoff of the lunar module from the moon hoaxers have criticised the fact that we cannot see the plume of the ascent engine. The Apollo believers think to have found an explanation for it by saying that the composition of the propellant is such that this plume is invisible. In this case, the Apollo believers would have to explain why this plume can be seen on the lateral thrusters in another sequence of the film, while these thrusters use the same propellant as the ascent engine. When the lunar module reaches the top of the image, we can see that it makes a sudden pitch over, that it is passing from a vertical attitude to a horizontal one. This is outright impossible. The lunar module cannot pitch excessively that way. It has still not reached the necessary horizontal speed which will allow to counter the lunar attraction, and therefore it cannot currently take a horizontal attitude. When the Saturn rocket is raising in the air, we never see it pitch that way. It pitches very slowly, progressively. If it had pitched like the way we see the lunar module do on the video of its ascent, it would have fallen back on Earth and crashed on it. This simplified schematic illustrates what happens when a rocket is launched. The rocket thrust has been represented with the yellow arrow, the gravity with the red arrow, and the gradually appearing centrifugal force with a green arrow. When a rocket is launched to be put into orbit, it first ascends vertically to extract itself from Earth's gravity and gain vertical speed. Then it starts turning to a more horizontal attitude to start gaining horizontal speed, but not brutally, but very gradually instead. It first takes a moderate horizontal attitude which allows it to gain horizontal speed. As it is gaining horizontal speed, a centrifugal force starts to appear, and this centrifugal force helps the rocket to counter Earth's gravity. So the rocket turns a little more horizontal, which allows it to gain still more horizontal speed. As the horizontal speed increases, so does the centrifugal force, which helps the more the rocket to counter Earth's attraction, which allows the rocket to turn more horizontal to gain still more horizontal speed, and so on. At the end of the process, the rocket ends in a completely horizontal attitude. Its horizontal speed is now the orbital speed, which allows to create a centrifugal force which is exactly equal to Earth's attraction, which means that the rocket has no more to give a vertical force to counter the Earth's attraction. The rocket can keep its orbital speed without having to produce a horizontal force, for in the void there's no resistance force to slow down the rocket. The rocket can naturally follow its orbit without having to use its engine. The change of attitude of the rocket from vertical to horizontal is very slow, progressive and regular. It can in no way be brutal. If the rocket, after its initial vertical ascent, was brutally turning a horizontal attitude, as it has not gained the horizontal speed allowing to produce a centrifugal force which counters Earth's attraction, it would start to fall back to Earth. As it is falling down, it would gain horizontal speed, but not fast enough to have reached the necessary centrifugal force allowing to counter Earth's attraction before it hits the ground. The crash is inevitable. After the pitch over, we can see the lunar module descend. It does not come from a move of the camera, but simply from the fact that the lunar module no more counters the lunar attraction, as it currently has a horizontal attitude, which means that its engine no more produces a force directed towards the moon. Its fall suddenly stops, which could only be explained that it has taken again a vertical attitude. Then we can see it makes a strange sinusoidal move with a grown amplitude, and if the operator had tried to follow the lunar module, we would not have seen a continuous move like what we see, but a discontinuous one instead, because of the command delay, and moreover, the operator would have tried to move the lunar module near the middle of the image and would not have kept it near its bottom. In fact, this sinusoidal move has an explanation. The first problem of the ascent stage is that, unlike the descent engine, the ascent engine was not gimbaled, and thus it could not be swiveled to remake the alignment of the thrust with the centre of mass. The second problem is that, unlike in the descent stage, there is only an oxidizer tank and a fuel tank in the ascent stage, and consequently the centre of mass was still more shifted in the ascent than in the descent. Consequently, there was a grown misalignment torque in the ascent, and this misalignment torque could only be compensated with the lateral thrusters, as these ones could not be throttled. A growing swaying move could not be avoided. The fact that the tank of the oxidizer is placed closer to the ascent engine is explained by the fact that the oxidizer has a greater density than the one of the fuel, 1.5 times greater. If they were placed at the same distance, the difference of density of the propellants would make the lunar module turn on the side of the oxidizer tank. At the beginning of the ascent, when the tanks are full, their contents are heavier than the containers, so the misalignment torque is limited. But as the tanks are emptying, the difference between the contents and the containers decreases, and consequently the centre of the mass of the lunar module shifts towards the fuel tank, with the consequence that the misalignment torque increases, as the lateral jets of the RCS cannot increase their frequency of correction of the misalignment torque. The consequence is that the amplitude of the oscillation of the lunar module progressively increases. The purpose of this animation is to make understand what happens and not to present the exact reality. Even if this was possible to correct the misalignment torque with the lateral thrusters, it still was uselessly wasting their propellant and complicating the guidance, for they are also used to modify the trajectory of the lunar module, whereas this propellant would have been saved if the ascent engine had been gimbaled. Clavius himself acknowledges this oscillating behaviour of the lunar module, and he says this on his site. As the off-axis thrust caused the ascent stage to rotate, the RCS jets fired to counter the rotation and return it to the correct attitude. This is why the films of the LM ascent seem to show a periodic swaying or oscillation. The RCS fought the off-axis ascent engine. And if ever the misalignment torque was becoming stronger than the counter torque that the lateral thrusters could provide, the ascent would fatally end. This is the logical command interface of the lateral thrusters, RCS, which can be found in the handbook of the lunar module. What we see about the vertical thrusters is really surprising. Each command activates two vertical thrusters directly opposed to each other on the same cluster. How can the RCS work when each command of the lateral vertical thrusters activates two vertical thrusters directly opposed to each other on the same cluster, thus cancelling their mutual effects? The document also allows a table of rotational manoeuvres which is less absurd, for the two thrusters activated by each command are not on the same cluster but on diagonally opposed clusters. This table contradicts the schematics we have seen, and even if it seems more coherent than schematics, it still has a big problem, and it would not have allowed to normally control the attitude of the lunar module. Indeed, each command acts both on the pitch and the roll. With this table, it is impossible to pitch without rolling and vice versa. In fact, pitching without rolling or rolling without pitching cannot be done with two thrusters only. 4 thrusters are required to make it. For instance, this schema allows how the lunar module can be pitched up by finding the thrusters A4D, B1D, A3U and BTU, and the roll command also needs 4 thrusters. The interface of command of the vertical thrusters had 3 commands, which could be either positive or negative, so it was in fact making 6 different commands. The pitch, rotation around the y-axis, the roll, rotation around the z-axis, and the vertical translation command, X trans L. And the interface command of the horizontal thrusters had 3 commands, which could be either positive or negative, so it was in fact making 6 different commands. The yaw, rotation around the x-axis, a translation on the right or the left, a translation forward or backward. In order to communicate with the LGC, the AGC was using channels on it which could send information to the LGC, or from which it could get information from it. In order to write into a channel, the AGC had a write instruction. Normally there should have existed a channel with 12 bits to send the commands for controlling the RCS to the LGC. A bit to send a pitch command, a bit to send the sign of the pitch command, a bit to send a roll command, a bit to send the sign of the roll command, a bit to send a command of vertical translation, and a bit to send the sign of this vertical translation, a bit to send a yaw command, a bit to send the sign of this yaw command, a bit to send a translation along the y-axis, and a bit to send the sign of this command, a bit to send a translation along the z-axis, and a bit to send the sign of this command. But in fact, instead of that, there are 2 channels for controlling the RCS, with 8 bits on each of these channels, which means there are 16 commands sent to the LGC for controlling the RCS instead of 12. Instead of sending the normal commands of rotation and translation, 3 commands of rotation, either positive or negative, and 3 commands of translation, either positive or negative, these channels would allow the control of 16 thrusters of the RCS, and what the LGC does not allow. It would make no sense that the AGC would independently control the 16 thrusters of the RCS, for nothing would prevent it from activating thrusters which are incompatible. For instance, by setting the 8 bits of the two channels 5 and 6 to all ones, it would activate all the 16 thrusters of the RCS, which would mutually cancel their effects. If they all have the same thrust, the result is that the lunar module would not react to these thrusters, while it would uselessly waste the propellant of the RCS. That shows how absurd it would be that the AGC could individually command the thrusters of the RCS without control from the LGC. Moreover, the routine which controls the attitude of the lunar module does not even write into these channels, which means that it does not try to control the lateral thrusters, and these channels could not even be used by the LGC. It simply means that the AGC has no control of the RCS. The LGC could automatically set the engine on or off, what the astronauts could do also manually with the engine start-stop button, the engine on and engine off commands. The AGC had an access to the command engine on and engine off through 2 bits in the channel 11. Writing a 1 in the bit 13 of this channel was allowed to send an engine on command, that is to set the engine on, and writing a 1 in the bit 14 of this channel was allowed to send an engine off command, that is to set the engine off. Now, how was the thrust adjusted? The way that it was adjusted is described in the technical manual under the lunar module. The increased throttle and decreased throttle commands were inputs to a counter. The increased throttle command was allowed to increment the counter, and the decreased throttle command was allowed to decrement the counter. The output of the counter was allowed to control the thrust of the engine when it was the LGC which had the control of the thrust, that is, when the engine control mode was in auto. Sending a pulse on the increased throttle command was allowed to increment the counter, and thus to increase the thrust of the engine. The documentation says that the pulse on increased throttle was increasing the thrust by 2.7 pounds. Sending a pulse on the increased throttle command was allowing to increment the counter, and thus to increase the thrust of the engine. The documentation says that the pulse on increased throttle was increasing the thrust by 2.7 pounds. So increasing the thrust was done by sending trains of pulses on the increased throttle command, while decreasing the thrust was done by sending trains of pulses on the decreased throttle command. The maximum thrust of the main descent engine was 9,900 pounds, and the minimum thrust was 1,280 pounds. So, if each pulse on the increased throttle and the decreased throttle commands was making a variation of 2.7 pounds of the thrust, it means that the thrust could be adjusted by 9,900 minus 1,280 divided by 2.7 equaling 3,192 steps. This could be made with the command of 12 bits. 12 bits represents a value of 4,096. It means there should be an output channel of the AGC on which 12 bits are reserved for the control of the thrust. It would then work this way. When the AGC wants to set a desired level for the thrust, it would write the corresponding level on 12 consecutive bits of a dedicated channel. The LGC would then use this desired thrust to compare it with the current thrust. If the desired thrust is greater than the current thrust, the LGC would send desired thrust minus current thrust pulses on the command increase throttle to increase the counter controlling the thrust by this value. If the desired thrust is smaller than the current thrust, the LGC would send current thrust minus desired thrust pulses on the command decrease throttle to decrease the counter controlling the thrust by this value. This way, the current thrust would be maintained equal to the desired thrust of the AGC. But there was no channel which was allowing the AGC to control the thrust of the main engine. Yet the 12 bits preceding the bits of the engine on, bit 13, and the engine off, bit 14, could perfectly have been used by the AGC to specify the desired level of thrust. Instead of that, these bits are only used for light indicators. The power descent could perfectly be done without these light indicators, but it could not be done if the AGC could not control the thrust of the main engine. The thrust is set at a maximum at the beginning of the powered descent and decreased after the braking phase, and when the lunar module is moving over the lunar surface in order to find a spot to land on, the thrust is continually adjusted to compensate the lunar attraction as the weight of the lunar module decreases. Moreover, there are plenty of spare bits on other channels which could have been used for these light indicators. The program Burn Baby Burn, which is called the start of the power descent, should put the engine at full thrust, but if it effectively sets the engine on by setting the bit 13 of channel 11, it does nothing to change its thrust, which is not surprising since it has no command to do it. So, the AGC has no way to control the thrust of the main engine. There was no way with the control of either the RCS or the thrust of the main engine that was making the power descent completely impossible. And that was also making the power descent impossible for the same reason, and the power descent was still more needed in the RCS than the power descent, for it has to compensate the misalignment torque, what the power descent did not need to do, for unlike the ascent engine, the descent engine was gimbaled and could thus be swiveled to remake the alignment of the line of the thrust with the centre of mass. In fact, the engineers have given many hints that the missions were fake. All the anomaly reports of the missions are nothing but jokes, but the more tasty jokes are what happened in the descent of Apollo 11 and Apollo 14, with the problem of the 1202 alarm for Apollo 11 and the problem of the abort button on Apollo 14, that people consider simple incidents which could be solved, which are in fact hilarious jokes, as you are going to see.